Hi, everybody. So I'm Alan. I'll be talking about MCDC. What is it? Why is it important? And how did I enable it with LLVM? So in order to really understand MCDC, we've got to recap a few topics. LLVM supports this notion of source-based code coverage. And ideally, you want to run code coverage, right? You want to make sure that every line of your code has an associated test. Code coverage will tell you that. You don't want code going out with an untested function because customers in the field could easily run into lurking bugs in that code. And so it just makes good practical sense as a best practice to run code coverage. LLVM currently supports 4 criteria for code coverage that will tell you your function coverage, how many functions are covered, for example, line coverage, region coverage, and branch coverage, which is a criterion that I added early last year. So this code coverage is called source-based because it's tied directly to the abstract syntax tree representation of the source code. It's very accurate in that way. When you run the code coverage flow in LLVM and you visualize it, you'll see a source level view that looks something like this. This view tells you the line count, it tells you the region count that's been executed, and it also tells you the branch coverage count. What most people are interested in, though, is the summary review. If you can generate a code coverage report that tells you an accumulation across these criteria for your whole project. So, how many files, how many functions in all of the source code of your project are covered, for example. Now, I mentioned branch coverage, which was added early last year. So in order to really understand MCDC, we've got to recap what that is a little bit. What is branch coverage? Branch coverage pertains to testing conditions in your code. So in this case, a condition is a leaf-level Boolean expression that can't be broken down further into simpler expressions. So if we have an if statement like this one, where x is checked to be equal to 2, that's a single condition. And in the code, a condition yields a branch instruction, and the condition can evaluate to either true or false, which affects the branch. Building on top of this a little further is the notion of a decision. A decision point in your code is basically a Boolean expression that can be composed of 1 or more conditions and 0 or more logical operators. So in this case, this decision is based on 2 conditions. A decision without a logical operator is trivially a condition. That can also be a decision. So in LLVM, when you turn on branch coverage, it'll provide a measurement for condition outcomes. In other words, how many times did the condition evaluate to true or false and affect the branch that's generated from that. So branch coverage is very useful, especially in an embedded setting where it's often required. But it also tells you, how a more complete picture of the path coverage through your code through control flow. The LLVM implementation of branch coverage is very similar to gcov, which gives you a very granular representation of conditions. But other vendors who support branch coverage, sometimes they focus only on decisions. That's all they care about. But there are limits to branch coverage, however. We consider this case, in this function, we've got 3 conditions, A, B, and C, and 2 logical operators. So when testing this, how can we be sure that we've covered all the critical paths through that control flow? Well, here are all the paths to the control flow. And this accounts also in C and C++, there's short circuit semantic behavior around logical operators. So if A evaluates to false, for example, the B condition is never evaluated. So these are the possible paths through the control flow. Well, if we rely on branch coverage alone, we can achieve 100% branch coverage by testing 3 of these paths. So for some, that may be good enough, but we're leaving out critical paths here. Now, an alternative to this is you can exhaustively test all the possible paths, all the possible cases through the control flow. But that gets very tedious, especially because it scales exponentially. So MCDC kind of offers an alternative to this. So let's talk about what that is. So MCDC, it stands for Modified Condition Decision Coverage. Strictly speaking, it's a metric pertaining to conditions in a Boolean expression decision, in which each condition has been shown to affect that decision outcome independently. And I'll go into this in a lot more depth. It can be a little vague when you just read the definition. It's called modified because we can change the test input to yield different test path flows through the Boolean expression, through the control flow. And ordinarily, as I mentioned, given n conditions, there are 2 to the n possible test paths. This is exponential. MCDC is a linear approach. It requires only n+1 test paths to be executed. So it answers the question, what really is a critical path that you're concerned about measuring? So if measuring all the possible paths is too tedious, MCDC gives you an alternative that's more practical to test and linear. So let's look at an example of what MCDC entails. Returning again to this example, this Boolean expression here with 3 conditions. And again, this is the list of possible test paths through this control flow. And another name for the test path is a test vector. So we'll call it test vectors. Now, given this, MCDC is achieved if we can find what we call an independence pair for each condition. What's an independence pair? Well, it's 2 test vectors for which, as the condition outcome is varied between true and false, the result is also varied between true and false. In other words, the condition outcome affects the decision result directly. And all the other condition outcomes are held as fixed or don't care if they're unevaluatable, as in the case with short circuit logical operators. So in this particular case, to show MCDC for condition A, we need to execute test vectors 1 and 3. That's because as we vary the outcome of condition A between true and false, the result also varies between true and false. The other conditions are held fixed, or in this case, there's don't cares there because there's unevaluatable cases. So for condition B, it's sufficient for MCDC to test vectors 3 and 5. Again, as we vary B's condition between true and false, the result also varies between true and false. The other conditions are held fixed. In this case, A is held at true in both cases. C is held false, and for test vector 3, it's a don't care. It's masked out. And similarly, for condition C, we need to execute test vectors 1 and 2. Again, as we vary C's outcome between true and false, the decision result also varies between true and false. The other conditions are held fixed. So MCDC is therefore achieved if we execute test vectors 1, 2, 3, and 5. Similarly, we could execute 4 and 5 as well for condition C. It also satisfies the condition, but it's optional. So if you execute the full if you execute the full code coverage flow, you'll see something like this, where MCDC is just simply a criterion that's added onto the end in an accumulation of all the code in your project, just like the other criteria. Here, MCDC is simply a measure of the independence pairs that we were able to find for each condition in a Boolean expression. If you drill into the source level view a bit deeper, for debug purposes, you'll see the existing branch coverage view, which tells you the true and false outcomes of each condition. But you'll also see an extended region here for the MCDC information for this Boolean expression, starting with a mapping of each condition in the source code where it's located, and an alias just to make it easier to represent in the report. So we'll call condition A C1, B C2, and C C3, just to make it a little easier. The MCDC analysis will also tell you the executed test vectors, and it'll tell you the overall metric. Was an independence pair found for each condition or not? And in this case, it only found pairs for conditions 1 and 2. So it's about 2/3 covered. So when is MCDC really important? Well, fundamentally, it's required by safety-critical embedded application development standards, right? So especially automotive and aviation, but it's also applicable to railway and industrial, medical, and space technology. So the sky is literally the limit here. A lot of people rely on MCDC because it's not the exhaustive full test path search that you think you might need to do, but it's a lot more comprehensive than just plain branch coverage by itself. And in general, it's a good practice anyway, I believe, if you can do it, to use MCDC in addition to standard branch coverage in your own personal development. And LLVM is being increasingly used in the embedded space, and so supporting MCDC makes sense to facilitate embedded development. At TI, a lot of our customers have complained about the third-party tools that they use to set up MCDC. They're cumbersome to set up and run and execute. What better than to build code coverage and MCDC into the compiler itself that you're using, so you can just turn it on and get the information out. So how do we go about implementing this in LLVM? How does it all work? Well, first we had to look at what has been done. How do these other vendors actually support MCDC? Most support a log-based approach, which is very robust. In this case, the code is simply instrumented to track condition outcomes through the execution of the control flow. The overall data is output usually to a file, and that file is then fed in as input later in the flow to an offline tool. This can be kind of cumbersome for build systems to track different output files and input files, and it's something that we'd like to work around, but this is probably the most common approach. The only issue is, today LLVM really only understands raw profile counter data in memory. But counters, as traditionally understood, really aren't suitable for tracking test vector execution. In the first place, they don't scale very well. They're big, even if you adjust the size. And we're really not interested in how many times a test vector has been executed. We're only really interested in that it was executed to begin with. So we really only need a bit of data for this. So what we decided to do is support the log-based approach, but without outputting data to a separate file. We'd leveraged the Clang-based instrumentation passes, which are very efficient already, to track the condition outcomes in the execution, and then find a way to efficiently store the data in memory where it can be extracted by the coverage tools, just like other coverage data is. So what we came up with was the concept of a bitmap coverage object. The idea here is to track a global bitmap in memory in which each bit simply represents an executed test vector, and that's it. It's instrumented for a boolean expression with two or more conditions, and it's treated like profile counters. It's handled in the backend like counters are, but it's handled slightly differently and kept in a separate section of memory. And this is fundamental. It's variable length. It depends on the number of possible test vectors for a Boolean expression. So in our case, it can be between 8 bits or up to 2 to the n bits, but it's bits. It's not bytes. It's not counters. So a Boolean expression that has 2 to 3 conditions in it takes only a byte. And in practice, in most embedded applications, this is all you'll see. You won't see anything more than about 3 conditions in an expression. A 4-condition Boolean expression would require twice that amount. 5 would require that. It scales by bits exponentially, but we think it's safe to cap it at 6 just to keep everything small, relatively small and manageable. So how do these bits map to test vectors? Well, let's look at an example. Here's another Boolean expression, this time with 4 conditions in it, and 3 logical operators. And this is the list of possible test vectors through that code, test paths. Now you can think of the true and false evaluations, the true and false outcomes of each condition, is simply a binary map, where each condition, true, is simply a 1-bit, and each false condition is simply a 0 bit. And if it's skipped, if it's unevaluatable, you just leave that at 0. What you end up here is with the evaluation of all the conditions, you end up with a unique ID that identifies that test vector. And so basically, we instrument the evaluation of each condition in an expression. The resulting value gives us the index into the global bitmap. So in this case, if test vector 2 is executed, that gives us a decimal value of 11, so we simply set the 11th bit in the bitmap. If test vector 3 is executed, it's binary value 10, we set the 10th bit in the bitmap. Simple as that. And across all of the Boolean expressions in a function, across all the functions, that data can just be glommed together as one large bitmap. When this is actually executed during runtime, the runtime profile merging simply does a bitwise OR between the bitmaps to accumulate the data. So there's no risk of overflow or anything like that associated with counters, for example. The prof data tool works the same way when you merge profiles. So one thing that we have to do also is ensure that we can map the bitmap to the source code. We talked about before, source-based code coverage requires a mapping to the abstract syntax tree representation. So I introduced a new decision mapping type for the counter mapping regions that does this. It ties the Boolean expression and the bitmap to the source code with an index and contains the number of conditions too. But the other thing that I chose to do is extend the existing notion of branch regions to include a notion of an ID. And I did this to represent the control flow through a Boolean expression. Now, why did I do this? Well, first of all, if we give each condition an ID, like 1, 2, 3, or 4, and then based on its evaluation, we can give it another ID. Where does it go next in the control flow? How does it evaluate it? It evaluates to false, it evaluates to true. What condition does it look at next? And the reason why I did this was because I wanted to keep language-specific information away from LLVM Cov, the visualization utility, but I also wanted to give it a way to reconstruct the list of possible test vectors. So this allows it to do that. Now, when you actually visualize this in LLVM Cov will see the regions that we've generated, the decision region and the branch region, and it simply does the reverse. It extracts the IDs from the branch regions, reconstructs the table of possible test vectors, and then it looks at the decision region, extracts that index, it gets the global bitmap, and maps those set bits back to the table. Once it knows the list of executed test vectors, as in this case, let's say we've executed only 3, it then performs an analysis for MCDC across each condition. Now, this is the most computationally expensive part of the algorithm. This is something that's well known to other vendors as well. But when you're dealing with 2 to 3 conditions in a Boolean expression, it's not that bad. What it'll do is it'll look for an independence pair. It'll do that for condition A. It won't be able to find one for A out of this set because one of the criteria is not satisfied. Condition D is not held fixed. It'll look for B and C, and it won't be able to find an independence pair out of this set of executed test vectors either. But it will for D. 2 and 3 satisfy the condition. And so in this particular case, only one condition is covered by MCDC, yielding an expression metric coverage metric of 25%. So the current state of this implementation is complete. I'm in the process of upstreaming the work. I've got a fabricator review, which I'll probably split up to make it a little bit more granular, but if you're interested, you could go here and take a look. And the goal is for it to be included with stock source-based code coverage, but enabled with a command line option. So if you don't want the extra instrumentation, you don't have to have it. But there are a lot of ways to improve this for given many different use cases. I'm working primarily with embedded use cases, but there are lots of ways to improve this. And so if you're interested in being involved with that or improving branch coverage, which already exists there, please contact me. So Thank you very much for your time.
Thank you, Ellen. So now we are open to the questions.
Do you use it only to visualize the coverage or to reason about it automatically in some way?
It's usually just for visualization or for tracking data. So you don't, if I understand your question correctly, you don't like feed it back in a PGO scenario.
My interest is whether we can use this kind of information to guide fuzzy.
Potentially. I think branch coverage might be more useful in that case, but you could use MCDC for that.
How well does the current coverage tooling handle templates and other, mostly just templates?
It's pretty good from what I understand. It'll track different instantiations of the template, and it will do that for MCDC as well. So. Yeah, Peter.
Have you measured the runtime overhead of the MCDC instrumentation?
I knew that question was going to come up. No, I haven't. As I mentioned before, most of our cases are about 2 to 3 conditions. It's not a huge impact, but I don't have numbers for you at this point. One thing that we did care more about was code size impact, because we're dealing with an embedded device with tight memory restrictions. And in that case, if you're interested, the code impact was less than 0.5%, and the data impact was less than 0.5%. It really was pretty negligible. But
Your use case is most likely single-threaded. Do you know how this instrumentation behaves in multiple threads?
it should be fine in that scenario. Each index is tracked independently in a function in its own thread, in its own stack. I don't see any obstacle to using in a multi-threaded environment.
Maybe just a comment, if you allow me. We're desperately looking for more signals to guide fuzzing. And of course, we use edges. We have been using them for 15 years in fuzzing. We need more. And if you have any reason to think this helps fuzzing, we want it.
Okay. Yeah, we can explore that offline and see if it can benefit you.
You might have covered this. I missed the first couple minutes. How do you stop the optimizations like select and evaluations like if such and such, then A equals 0, else A equals 1, and they just become simple computations. They don't actually take a branch path. So how do you stop the optimizer from erasing these branches and getting rid of things you're trying to cover?
Well, there's two aspects to that. So the first aspect is code coverage. The source-based code coverage is fundamentally a measure of the source code. So it might yield different code in a different optimization scenario. You want to make sure that your source code is covered fundamentally, whatever gets generated from that. The second aspect of that is optimizations don't impact code coverage significantly with LLVM. It's very accurate in that regard. If we instrument code, it might obstruct an optimization or prevent it from happening. And that's good because that gives us an accurate measurement of the coverage. If we were dealing from a purely hardware level point of view, we might find that optimization impacts code coverage in a negative way, but that doesn't happen here.
Thank you, Ellen.
Thank you.
Yeah. So,